Hello students, welcome to Tuteetute. In our last sessions, we have understood the questions from other subjects. In this session, we will understand the concepts from the bridges. Okay, so in electrical and electronic measurements, so we have the bridges concepts. So these questions generally will be simple. So we definitely can expect one or two questions. So this one or two questions from the bridges, if you are electrical, electronics or mechanical, so this one or two questions from the bridges, so you can definitely answer from this entire session. Okay, so let's see the first question. Hayes bridge is used to measure. Okay, so Hayes bridge they are asking. So Hayes bridge, why we are using? Let's see the options. Very low resistance, inductance of coil, capacitance of the capacitor, impedance of a circuit. Okay, so what is this Hayes bridge? So we need to remember some of the bridges. Okay, so Hayes bridge generally will be used for the high inductance. Okay, so high inductance measurement. Okay, so high inductance, or when inductance is high, then high Q factor measurement. Okay, so high Q factor measurement. Okay, so like this, these are the two things. Okay, so in inductance of coil, very low resistance. So according to these options, what we have to choose? This Hayes bridge will be used for the inductance measurement. Okay, so inductance of coil, this is the answer. Okay, so this is impedance, this is capacitance, this is resistance. So only inductance is there, but they try to just confuse you by using this question. Okay, so here we need to remember some of the questions. So Maxwell's inductance capacitance bridge. Okay, so inductance capacitance bridge. So generally, why we are using this Maxwell's inductance capacitance bridge? So we are using this one for the medium inductance measurement. Okay, so medium inductance measurement or medium Q factor measurement. How we have to remember this one? Medium Q factor measurement. See, you might have understood the classes already. I have given in the classes already these all. So any measurement faculty will tell you this one. Okay, so remember this M and this M. Okay, so if Maxwell's inductance capacitance bridge, medium inductance measurement. Okay, so Hayes bridge, high inductance measurement. Okay, so this we need to remember. Okay, and similar to this, okay, Anderson's bridge. Okay, so Anderson's bridge, why we are using? Anderson's bridge we are using for the accurate Q factor measurement or accurate inductance measurement. Okay, so accurate inductance measurement or accurate Q factor measurement. Okay, so accurate Q factor measurement, you need to remember like this. Okay, so then you can easily answer, no need to concentrate more on this. Okay, so not only this, Owen's bridge. Okay, so Owen's bridge, why we are using Owen's bridge? So Owen's bridge we are using for the incremental inductance measurement. Okay, so incremental inductance measurements. Okay, so incremental inductance, like any small change in inductance. Okay, so like any small change in inductance, if you want to measure, so that means any small change, any small increment in inductance, we need to measure using Owen's bridge. Okay, so if it is a medium inductance, then we can use not medium. If it is a high inductance, then we can use the Hayes bridge. Okay, so then Maxwell's bridge will be using for the medium inductance measurement. So like this, some of the bridges we need to remember. Okay, so total there will be 10 bridges. So these 10 bridges definitely they will give 1 or 2 in our exam. Okay, so these 10 bridges definitely 1 or 2 questions will be there from these 10 bridges. Why we are using that bridges? Application of that bridge majorly they are asking. Okay, so anyhow answer for this question is inductance of coil. The next question, the bridge most suited for the measurement of a 4-terminal resistance in the range of 0.001 to 0.1 ohm. Okay, so whenever you see this low resistance less than 0.1 ohms of resistance, means it is less resistance or very small resistance, we need to use this Kelvin's double bridge. Okay, so why they have mentioned this 4-terminal resistance? Just to confuse you, I will tell you why we have to consider this as a 4-terminal resistance. See, for example, this is the resistance we have, so which is having a 0.1 ohms. Okay, so this is the resistance which is having 0.1 ohm. So this is also a wire, right? So this wire also will be having rho L divided by A. So this wire is having some resistivity, this wire is having certain length, and this wire is having a certain area of cross section. Definitely resistance will be there. If it is also 0.1 ohm, 0.1 ohm this side also. That means terminals also are leads. These are called leads. These leads also having certain resistance. Understanding? So whenever leads also having resistance, if you try to connect using one multimeter, definitely you will get 0.1 plus 0.1 plus 0.1, you will be getting as 0.3 ohms. That means this is the measured value of resistance. What is the true value of resistance? True value of resistance is 0.1. If you calculate the error, what you will be getting? Error equals to measured value. Remember this also, okay? So every time error calculation is nothing but measured value minus true value. 0.3 minus 0.1, so that means 0.2 it is in terms of ohms error. Okay, so percentage error you have to calculate. Okay, so percentage error means, remember, error divided by, okay, so error divided by, with what we have to compare? We need to compare with the true value. Okay, so error value divided by true value of measurement. Okay, so that means 0.2 divided by 0.1 into 100, that means 200 it is. Okay, so 100 into 2 it is, then it is 200. Percentage error is nothing but 200 percentage. See, this is very huge error, right? That's why we cannot use Wheatstone bridge, we cannot use Megger, or we cannot use multimeter or any other method to this. So that's why whenever low resistance is there, this lead resistances we should not consider. Only the actual value of resistance we have to measure. Okay, so that's why what we have to use, we have to use this Kelvin's double bridge. Okay, so anyhow in Kelvin's double bridge, so we have certain method. Okay, so we will be connecting, so two kinds of balances will be there in the Kelvin's double bridge. Internally we will be balancing, then external arms also we will be balancing, then we will be getting so only this value of resistance. Okay, so that's how. Even formula also will be there. If you are from electrical, you need to definitely learn this. Okay, so that formula you have to remember. Okay, so anyhow error is 200%, so we should not use normal method for the low resistance measurement. That's why what we need to do is a smaller resistance, instead of representing as a 2 terminal resistance, we will be representing with 4 terminal resistance. Okay, so these two terminals are called current terminals or current leads. Okay, so current leads, and these two are called voltage leads. Okay, so voltage leads. So these voltage leads are having a very less length. Okay, so that means when length is less, then resistance of this leads will be less. Okay, but to calculate the current, so there is no problem. If you want to calculate the voltage, then these terminals we have to use. Okay, so to check the voltage across this voltage leads we have to use. To check the current, we need to use the current leads. Okay, so these are the 4 terminals, not 2 terminals. So that's why a small resistance, okay, so small resistance we need to use like a 4 terminal resistance. Okay, so 4 terminal resistance. Medium resistance we have to use it as a 2 terminal resistance. Okay, so and large resistance, so we need to consider as 3 terminal resistance. Okay, so this we need to remember. Okay, so 3 terminal resistance means how you need to consider. So this is the high resistance or very high resistance. So we will be having another terminal also. Why we need to consider like this? Because for any, just like an insulator, okay, for insulator there will be body resistance and surface resistance. Similar to that, for the high resistance also, you might have, if you have done the lab, okay, so we will be using one of the resistance which is having up to rotation like this. Okay, so it will be changed. That means this position we will be changing like this. Okay, so that is the representation. It will be having 3 terminals. Okay, so if you have remember in our labs, okay, so there will be 3 terminals like this. For the high resistance there will be variable resistance which we can change like this. If you connect between these two, so there will be one resistance is coming. Between these two, if you connect, another resistance will be coming. Okay, so like that. So if you have remember, that's okay. Otherwise no need now. Okay, so leave it. Next question, the bridge method commonly used for finding mutual inductance is, okay. See, this question also they have asked in the ECE, in the AP state GENCO they have asked, okay. See the options, Heaviside Campbell's bridge, Shearing's bridge, DSRT bridge, Wien's bridge. So they are asking about mutual inductance measurement. See, for self-inductance measurement, we have this Maxwell's inductance capacitance bridge, Hayes bridge, Owen's bridge, Anderson's bridge, and Maxwell's bridge also we have, okay, Maxwell's inductance bridge. But Maxwell's inductance bridge is having certain disadvantages, that's why we are not using, okay. So, and these other bridges, why we are using, we need to understand, okay. Remember these points, okay, whatever I am giving. Wien's bridge we are using for the frequency measurement. Okay, so frequency measurement. Whose frequency? Source frequency measurement. Okay, source frequency. So like unknown source, if any unknown source is there, for that unknown AC source, if you want to know the frequency of that source, we need to connect that one in the Wien's bridge and get the balance condition and find out the frequency. Okay, so that is the one. Remember these points. Okay, so DSRT bridge we are using for the capacitance measurement. Okay, so capacitance measurement. Okay, so next one is Shearing's bridge. Okay, so Shearing's bridge is having so many advantages. Okay, so many measurements we can do. So Shearing's bridge we are using for the dielectric loss. Okay, so dielectric loss measurement. Okay, so see, from the Shearing's bridge we can even measure the capacitance from we can measure the inductance also, and similar to that. Okay, so dielectric loss, not only that, loss tangent. Okay, so loss tangent we can measure, so that means tan delta. Okay, so this also we can measure. Okay, so not only this. Okay, so charge, by using so Shearing's bridge we can use the charge measurement. Okay, so charge means Q. Okay, so not this Q. Okay, so not Q factor, it's a charge Q. Okay, so this also we can measure. Okay, so majorly these questions will be there. So and I am also expecting this question from the next examination. Okay, your GENCO examination. Okay, so Heaviside Campbell's bridge we are using so for the mutual inductance measurement. Okay, so mutual inductance measurement we are using mutual inductance measurements. Okay, so mutual inductance measurement. Okay, mutual inductance measurement and capacitance measurement. Okay, so mutual inductance measurement and capacitance measurement we are using. So this Heaviside Campbell's bridge. Okay, so this is all important. So not only this. Okay, so I have already explained about see here 4 bridges are there here, and similar to this here also we are having 5 or 6 bridges we have just understood. Okay, so remember these all things. Okay, so not only this, 1 or 2 extra also there. Okay, so whenever you study the classes at that time you understand the remaining concepts also. Okay, so on the next question, the zero adjustment is done in a series type ohm meter is. Okay, see, generally if ohm meters and Megger, these all things in deep you might have not studied. Okay, so but if you see the construction of this ohm meter, series ohm meter, so what we need to do is the zero adjustment we have to do for the series type of ohm meter. Okay, so how we are doing means, see, changing the shunt resistance value connected across the meter movement. Okay, so remember this one. So this is directly, so there is certain problem we are getting whenever you are designing this series ohm meter. That time what you need to do is so change the shunt resistance value connected across the meter movement. So then you need to do the zero adjustment. Okay, so that's what so we need to understand. Okay, so see, these are all ohm meter generally we are using for the medium resistance measurement. Okay, so similar to ohm meter, similar to this series ohm meter, so we are having the shunt ohm meter also. Okay, so shunt ohm meter also. So for the high resistance measurement, Megger we are having. Okay, so Megger we are having, and similar to this. Okay, so there are loss of charge method. Okay, so direct deflection method. So one by one. Okay, so you just need to understand the concept of this one. Okay, if you are from electrical, so concentrate on these 2 or 3. Okay, so I am just telling you direct deflection method. Okay, so direct deflection method. Okay, so and potentiometric method. Okay, so potentiometric method for the resistance measurement only. Okay, so potentiometric method. So next one is loss of charge method. Okay, so loss of charge method. Okay, so next one is substitution method. Okay, substitution method. Okay, so substitution method. Okay, so these are the things we need to concentrate definitely. So mostly the question will be coming from these areas. Okay, so because so these all methods generally useful. Okay, if you are working in the underground cables, so you need to work on this loss of charge method sometimes. Okay, so and there are meggers also applications we have in the underground cable. Otherwise, so you will be internally. Okay, so internally in the power plant. So if you are working at that time, some of the devices also you need to carry for the measurement purpose. Okay, so that's why these methods are important for us. Okay, so anyway, answer for this question is changing shunt resistance value connected across the meter movement. Okay, the next question, low Q inductance is measured by. Okay, so see this question, low Q measurement they are asking. Okay, so one thing is Hayes bridge, so you know already high inductance measurement. So Wien's bridge, you know, so it will be used for the frequency measurement. Okay, so Maxwell's bridge, so generally used for the medium inductance measurement. Okay, so medium inductance measurement. So what is this Anderson's bridge? Anderson's bridge will be using for the accurate inductance measurement. Okay, so there is directly, so this low Q inductance. Okay, so low Q, what is the Q factor? Omega L divided by R. Okay, so when low Q means, so directly inductance also low. Inductance low means very small changes will be there. Okay, so small changes will be there. So that means you need to calculate accurately. That's why, so for this question answer is Anderson's bridge, but they should not ask like low Q inductance. Okay, so if so low Q, if low Q, so we don't use this kind of coils. So when Q factor of that coil or inductance of that coil is very less means it is having more losses. Okay, so more losses. So that's why low Q coils we will not be considering. Okay, so, but it is unknown value generally, unknown coil actually. So that's why they might have given like this. Okay, but answer for this question is Anderson's bridge. Okay, so in some of the books it is like Maxwell's bridge, but don't consider like that. Okay, so this is Anderson's bridge we have to use. Okay, next one, identify the instrument that does not exist. Okay, so identify the instrument that does not exist. This is the ECE question. Dynamometer type of ammeter. Okay, so dynamometer type of wattmeter, moving iron voltmeter, moving iron wattmeter. Everything looks good only, right? But you see, so one thing is three instruments we have studied in the basic instruments. One is PMMC, second one is moving iron, third one is dynamometer type of instrument. Okay, so dynamometer type of instrument. Okay, so dynamometer type. See here, for the PMMC we can use this one as the ammeter and we can use this one as the voltmeter. Okay, so ammeter of DC, voltmeter of DC, only these two. Okay, AC we cannot use. PMMC is strictly only for the DC. Okay, so similar to this, so this can be used as ammeter, this can be used as voltmeter. In ammeter also we can use like DC and AC both, and similarly for the voltmeter also DC and AC. AC voltmeter or DC voltmeter we can use. Okay, so next one is dynamometer type of instrument. So ammeter we can use, dynamometer type of ammeter. Here some points we need to understand. Okay, so to convert dynamometer type of instrument as the ammeter, what you have to do? You have to connect so both current coil and potential coil in series with each other, and that combination we have to connect in series with the load. Okay, so this statement is important. Okay, if you are from electrical, definitely we can expect the questions from the dynamometer type of construction and designing of this dynamometer type of instrument as a ammeter, voltmeter and wattmeter. Okay, so here, so ammeter we can use, so this can be used for both AC and DC. Okay, similar to this voltmeter. Okay, if you connect the current coil and potential coil across the, so current coil and potential meter in series and across the load if you connect, so that will become as a voltmeter. So this also can be used for AC and DC. That means here one of the difference also we need to get. Okay, so when you are designing if you have designed ammeter PMMC, you can directly use it as a voltmeter. There is no problem. If you connect extra resistance, that's okay. If you design the ammeter, and you can directly use it as a voltmeter if it is a moving iron type of instrument also. Okay, so like only some extra precautions we have to take, but for the dynamometer type of instrument, if you design the ammeter, you need to change the connections, then only you can use it as a voltmeter. Okay, so that's how. And another one is wattmeter. Okay, so this is only the wattmeter we are using. So generally it is useful for the AC. Okay, so why AC? So because it's working on induction principle. Okay, so that's why we need to use it for the AC. DC power measurement generally we are using the, so we are measuring using the voltmeter and ammeter directly. Okay, so for the DC power measurement, what we will be using? PMMC instruments we will use. DC power or DC current or DC voltage, PMMC we will use. And for the AC current measurement, so moving iron we will use. For the AC voltage measurement, so moving iron we will use. And for the AC power measurement, so we will be using wattmeter. And 2 wattmeter method also, this kind of wattmeters, so 2 we have to connect. One in R phase, one in Y phase. Okay, so like that. Anyhow, in different session I will explain about wattmeters and energy meters and some of the other concepts also. Okay, so anyhow, in this session I am giving from the bridges and this, so instruments. Okay, so basic instruments from the ECE point of view only. Okay, so electrical sessions are different. Okay, I will give you even deeper concepts about so these measurements. Okay, so wattmeter is AC. What they are asking, see, dynamometer type of ammeter is present, this kind of instrument. Wattmeter also present. Moving iron voltmeter is present. So moving iron wattmeter not present. Okay, so wattmeter. Moving iron type of instrument, we cannot make it like a wattmeter. So here in the PMMC, how is the scale? Scale is linear. Okay, so scale is linear. How is the moving iron type of instrument scale? It follows a square law. Okay, so square it is. Okay, so that too at the beginning of the scale it is cramped scale. Okay, at the end of the scale, that means for the higher value of scale, so then it will be expanded scale. Okay, so here for the dynamometer type of instrument, so if it is an ammeter, okay, so it is a non-linear. Okay, so non-linear. So here also square or non-linear it is also. Okay, so non-linear because square means non-linear only. Okay, so voltmeter also non-linear. Okay, so for the wattmeter it is linear. Okay, so if you have understood the classes, you will get these points. Okay, for the wattmeter, linear scale is present even though it is a dynamometer type of instrument. Okay, so here only we have one question definitely for ECE. Okay, concentrate on these things, you will definitely have one question. Okay, so the next question, which one of the following meters is an integrating type of instrument? Okay, so we have 3 different kind of instruments. So those are indicating type. So next one is integrating type. Okay, so integrating type. So third one is recording type. Okay, so recording type. So these are the 3 kinds of instruments we have. So here energy meter will comes under so the integrating type of instrument. Ammeter is indicating type of instrument. Voltmeter is indicating type of instrument. Wattmeter is indicating. The indicating means it should have one scale like this, and on the scale there will be some readings and a pointer will be indicating. This pointer will indicate the value. Okay, so that's what indicating type of instrument. Integrating type of instrument means like now the value is 2. After some time it will become 3. After some time it will become 4. It's adding the values. For the previous value, new value will be adding. Okay, so like you have consumed already 200 units of energy. In these 2 days you have consumed 10 units extra. That means 210 it will come. That means 200 plus 10. Next again 5. 210 plus 5, that means whatever previous value is there, it is adding, it is integrating to this value. Okay, so that means integrating type of instrument. So you might have observed the energy meter. If you don't know, just stop the video and just go to so the energy meter, wherever you are, definitely there you can find the energy meter. So just check. Okay, so it will be moving slowly like this. Okay, so this will move after this 10 then it will be moving 1. So just like your meter. Okay, so in the vehicle you will be having the meter, right? Okay, so similar to that. Okay, so next recording type. What is this recording type? over a period of time it has to display the so all the values of that one. Okay, so majorly it will be like a waveform representation. Okay, so waveform, or it has to record some of the signals. Okay, so like it may be voice signal, or it may be any of the sound, or it may be any other kind of signals it has to record. Okay, so that means, so this is recording type of instrument. What is the example? We are having a CRO. Okay, so CRO, and in the cricket we are using, okay, so sneakometer. Okay, so sneakometer. So this is also a recording type of instrument. Otherwise, if you have any health problems related to heart, okay, so there will be, so one of the instrument they are keeping for that. Okay, so that is ECG, okay, so cardiogram it is. Okay, so next EEG also is there. Okay, so EEG means so encephalogram. Okay, so it will be used for the brain signals to measure. Okay, so that's what, so these are all the example for the recording type of instruments. Okay, so these are the previous questions, and some of the questions you might have already understood. Okay, so these are all, so some of the important concepts are, so these are, so anyway, in our next session we will understand from the different subject. Okay, all the best, thank you so much.